We are looking at embedding theorems. So we had that W1PRN is contained in LP star Rn, where when P is less than N and 1 by P star equals 1 by P minus 1 by N, and in fact it is contained in LQ of Rn for all Q belonging to P star. And then we saw that this is contained in LQ of Rn for all Q belonging to P infinity if P equals N. So now we want to look at the case when P is bigger than N. So this is the third case which we want to do, and here we state the theorem for this. Okay, so let N be less than P less than infinity, then we have the continuous inclusion W1P Rn in L infinity of Rn. There exists a constant C which depends only on N and P and is strictly positive, such that for all U in W1P Rn we have, and almost all xy in Rn, that means except for a set of measure 0, all pairs of points, you will have the following inequality: mod u of ux minus uy is less than or equal to c times mod u 1p Rn in mod 1 minus x minus mod of x minus y 1 minus n by p. So that means the functions are not just merely in L infinity of Rn, but they are actually continuous functions, and they are Helder continuous functions. So it's if you had 1 as the exponent instead of 1 minus n by p, that would be Lipschitz continuous function. Now we are having something less than 1, it's 1 minus n by p, and therefore that is called a Helder continuous function with Helder exponent 1 minus n by p. The same conclusions hold if Rn is replaced by Rn plus or by omega of class C1 with bounded boundary. Well, this is clear just because you can go to Rn by means of an extension operator and then you have the same results. The analogous result is also true for W1P0 omega for any open set omega. Okay, again because extension by 0 is always an extension operator and therefore we do not need. So proof, enough to prove for Rn. As I explained just now, extension operators will take care of the rest of the cases. Okay, so step 1, again we start with d of omega. So let u belong to d of Rn. So the fundamental theorem of calculus is always very important in all these cases. Even in the case p less than n, and for p equals n, we derived an inequality starting for u in d of Rn and then applying the fundamental theorem of calculus in some way. So we are going to apply it in a slightly different way now. So let Q be a cube with edges parallel to the coordinate axis. Assume 0 is in Q and let x belong to Q. Okay, so what is ux minus u of 0? By the fundamental theorem of calculus, this is integral 0 to 1 d by dt of u of t of x, t times x dt. Because if d by dt of something is just the end values you have to subtract. So u of 1x is u of x minus u of 0x is u of 0, and therefore you get this inequality here. So let u bar be the average mean or average of u over q. So what is u bar? This is equal to, so u bar is 1 over the Lebesgue measure of q, mod of q is the Lebesgue measure of q, integral over q, u of x, u of y dy. Okay, so then u bar minus u of 0. So I am just going to integrate this inequality over q and multiply by 1 by mod q. So that will give me u bar if I integrate the left hand side, that, and then u of 0 is a constant. So the average of a constant is itself. So u bar equals this. So that's equal to 1 by mod q integral over q, integral from 0 to 1, and then I am going to take d by dt of uxi. Now d by dt of u of tx by the chain rule is sigma I equals 1 to n du by dxi tx into txi. Okay, so that is the thing, and therefore I am going to write this equal to sigma integral over q integral, so sigma I equals 1 to n of xi du by dxi at tx dt dx. Okay. So now you take mod u minus u0, that is less than or equal to mod of xi will be less than r, because the cube with edges with edges parallel to the coordinate axis and of length r. I missed that. So r is the length of the side of the cube, 0 is in the cube, xi is there, so mod xi will be less than the length of the side of the cube. So that is less than or equal to r by mod q into integral over q sigma I equals 1 to n of integral 0 to 1 mod du by dxi at tx dt and then dx. Now mod q is r power n, so this is equal to 1 over r power n minus 1. So mod q equals r power n because cube of side r, and therefore this is 1 over r power n minus 1 integral. Now I am going to interchange the order of integration by Fubini's theorem. So integral 0 to 1 integral over q sigma I equals 1 to n mod du by dxi at tx dx dt. And that is equal to, I am going to make a change of variable 1 by r power n minus 1 integral 0 to 1, and then I am going to make tx equal to y. So t power n dx will be dy, because each xi will pick up one t, and therefore t power n dx is dx1 dx2 dxn, remember, therefore you get t power n dx equals dy, and therefore this will become integral over t times q of sigma I equals 1 to n of mod du by dxi at y, and then you get t power minus n dy. Now tq is contained in q because t is between 0 and 1, so 0 less than or equal to t less than or equal to 1, and therefore you have that, and now you apply Helder to the inner integral. So in the inner integral I will write that integral over tq mod du by dxi at y dy will be less than or equal to integral. Now I am going to write mod du by dxi power p whole power 1 by p, and that I will, it's over tq, but I am going to write tq is contained in q, so I can write less than or equal to integral over q, and then I have the function 1 which is here, which will give me the measure of this, that is tq mod tq power 1 by p prime. So if you substitute 1 by p plus 1 by p prime equal to 1, okay, so this is what we have. So now if you substitute that in the previous inequality, you get mod u bar minus u0 is less than or equal to, so you will get mod u 1p q, because I have sigma I equals 1 to, all of the powers will come there, and then by r power n minus 1 is already there, and then I will get what is mod of tq. So mod of tq equals t power n r power n, okay. So and then I am going to take 1 by p prime of that, so r power n by p prime will come there, and then integral 0 to 1 of dt will be t power n by p minus n, because there is a t power minus n already. Now I will get t power n by p prime, sorry, n by p prime minus n, and that is equal to, so if I r power n minus so r power n by p prime minus n will give you and n times 1 by p prime minus 1, which is minus 1 by p. So that is equal to r power 1 minus n by p. If you simplify this expression here, you get r power 1 minus n by p, and then this integral, if I integrate, this will just give you 1 minus n by p again, using the fact that 1 by p plus 1 by p prime equal to n, and then mod u 1p. So we have a nice relationship. Now by translation, this is valid in for any such cube Q. And any x in Q. Okay. So you have that for any such cube you have mod u bar minus u of x, okay, is less than or equal to r power 1 minus n by p by 1 minus n by p mod u 1 pq. Okay. Now if x and y belong to Q, you apply it both to x and to y, and then you get by the triangle inequality mod of ux minus uy is less than or equal to 2r power 1 minus n by p by 1 minus n by p into mod u 1 pq. Now, given xy in Rn, we can always find Q containing them and of side r equals 2 times mod x minus y. So, you can, given any 2 points, you take a big enough cube which is less than which of side 2 times x minus y, and that will contain x and y, and then this result is true, and therefore you have that substituting that you get mod ux minus uy is less than or equal to. So, you put everything in a big constant 2 by 1 minus n by p and 2 power 1 minus n by p, all these things, whatever you get, you put it in that, you get mod x minus y power 1 minus n by p. Okay, so this is for almost for all x y in R. So this is for u in d of Rn. So if u belongs to W1P of Rn, then there exists un in d of Rn such that un converges to u in W1P of Rn. And for a subsequence, pointwise almost everywhere. So then that will imply for all u in W1P of Rn. So you apply it to un and then you pass to the limit, you get mod ux minus y uy is less than or equal to c times mod x minus y power 1 minus n by p for all almost every xy. Okay, so this is the result. And also you have step 2. If u is in d of Rn, you have mod ux is less than or equal to mod u0 plus c times mod u 1pq, which is less than or equal to c times norm c dash times norm u 1pq, and that is less than or equal to c dash times norm u 1p Rn. And now you can again true for u in W1P of Rn by density. D omega is dense and therefore you have this. So this implies that W1P of Rn is contained in L infinity of R. So this completely proves the theorem here. Okay. So now you consider, let u belong to W2P of Rn. So this implies that u and du by dxi belong to W1P of Rn. 1 less than or equal to I less than or equal to a. Now if p is less than n, then u belongs to LP star Rn, du by dxi also belongs to LP star of Rn, and this implies that u belongs to W1P star of Rn. So assume P star is also less than n. So when will this happen? That is 1 by n is less than 1 by P star. P star is less than n, so 1 by n is less than 1. This is 1 by P minus 1 by n. Okay, and this implies that P is less than n by 2. because from this you will get 1 minus p minus 2 by n is bigger than 0, that is p is less than n by 2. And then, so this will imply that u belongs to L p star star or p double star Rn, and 1 by p double star is equal to 1 by p star minus 1 by n, and that is equal to 1 by p minus 2 by n. Okay. So, we can now iterate this to any positive integer, and then we can iterate all the theorems. So, by iterating arguments in the preceding theorems, we get the following. So, theorem, this is a complete Sobolev embedding theorem. Okay. So, let m be greater or equal to 1, an integer. Let 1 less than or equal to p less than infinity. So, 1. If 1 by p minus m by n is greater than 0, then WMPRN is continuously embedded in LQ of Rn, where 1 by q is equal to 1 by p minus m by n. 2. If 1 by p minus m by n equal to 0, then WMPRN is continuously embedded in LQ of Rn for all q belonging to p to infinity, last one excluded. And then 3, if 1 by p minus m by n is less than 0, then WMP of Rn is continuously embedded in L infinity of Rn. In the last case, let k be the integral part and theta the fractional part of m minus n by p, which is a positive number. Okay, 1 by p minus m is bigger than n by p from in the case 3, and therefore m minus n by p is positive. Okay, then there exists a C positive such that for all u in WMP of Rn, we have mod d alpha u in L infinity norm is less than C times norm u m p Rn for all mod alpha less than or equal to k. They are just bounded. Now, about the Helder continuity for almost all xy in Rn, you have mod d alpha u of x minus d alpha u of y is less than or equal to C times norm u m p Rn times and for all mod alpha equal to k mod x minus y to the theta, that is the fractional part. Okay. In particular, WMPRN is contained in Ck of R, and the kth derivatives are Helder continuous. The previous derivatives will be actually Lipschitz continuous for all m greater than n by p. Same results true for Rn plus or omega of class. Now you need Cm because you are iterating the condition. For first derivative you needed C1. So now for successive derivatives you have to include with bounded boundary, and for W1P MP 0 omega for any open set omega in Rn. So if omega is bounded in particular and sufficiently smooth, we have, and m is bigger than n by p, we have the WMP of omega is contained in Ck of omega bar. Okay, so this is the big theorem. Now remark, if m is bigger than n by p and mod alpha is strictly less than k, for mod alpha equal to k we said it is Helder continuous, and then implies that d alpha u is Lipschitz continuous, because any higher, the first derivative of d alpha u is in L infinity, it is bounded, and therefore d alpha u will be automatically Lipschitz continuous. It is only when you come to alpha equals mod k you cannot say anything about the next derivative, and therefore you only have Helder continuous. Okay, so that is just from the mean value theorem of which says if the derivative is bounded then the function is Lipschitz continuous. So this completes the study of the embedding theorems. Our next aim is to see which of these embeddings are going to be compact. Okay.